Hello everyone, let's move into the worksheet number 4 from the lecture number 4. So as a summary from the lecture number 4, we actually discuss about the current and the resistance and resistivity and the resistors basically, right? So what that means is after we talk about the potential difference in your lecture number 3, this is where we're going to connect that into the current voltage that we are experiencing in our laboratory, and also your all these circuits, home circuit or any circuits that we are working with will be related with the voltage and the current, right? So now current is defined as, current we use the letter I. Current is defined it as change of rate of charges. That means it's basically saying how many charges you can send per unit time. We call it as the current. So as soon as you see that that is the units of, you know that this is coulombs and time is in second, and coulomb divided by second, we have the new name, we call it as amperes, right? Or we usually use letter uppercase A for the amps. That is the units of the current. So now, now you know what is the current is. Now you already know what the voltage is. Now Ohms is the scientist that work with these two parameters, and he tried to do the experiment, and then he tried to produce the voltage as a function of current plot, right? So when we plot this one, that is the Ohm's law, Ohms. So what Ohm's law saying is that V and I are proportional to each other. That means if I plot in any circuit, if I plot voltage as a function of current, this should be a linear. And then if you take the slope of this one, it is a constant. That constant, we call it as the R. So that is the resistances. Now Ohm's law saying V is proportional to the current, and then V you will be able to write by using equal sign with some constant, and I, that constant we call it as the resistance, right? So resistance is the value of the resistor. Resistor is a device that resists the current, and resistance is the how much it will resist. That's the value, right? These words are different, right? So now always this resistance is the ratio to voltage over current, right? So now if any material obey this one, we call it as ohmic materials. Now that we discussed this everything in your lecture, ohmic materials, right? But some materials, like as example, if you take the platinum, maybe light bulb, right? So light bulb will not follow this feature. Light bulb will follow, if I draw it voltage as a function of current, it may be like going like this, right? So those materials are not obeying this V equal IR, then those materials we call it as non-ohmic materials. Okay? Non-ohmic. So I will not go further from that on that, because I am going to plan to discuss a little bit about this resistance throughout the worksheet and how these things going to change, right? So now we have the resistance R, right? So this R you are not able to change by changing V and I, because it's always V to I ratio. But R can be changed in manufacturing process. R, that value can be calculated by using this formula. What this formula mean to you, if I have a resistance, we'll say I have a cylindrical kind of resistance, resistor, this kind of things, right? If that resistor has length L, that's what the manufacturer do when they create a resistor, they can change the L. If you increase the L, R going to be increased, right? Because it is on your numerator, right? Now, if you check the cross-sectional area of this one, we know that if it is a cylinder, it is a pi and radius power 2. So now, if you keep increase in cross-sectional area, you see that it is in denominator, then your R going to be decrease. Resistance will be decreasing by increasing cross-sectional area, right? So now other parameter you have it in here is rho. Rho is, you remember that we use it for the density earlier in your 116 class, but here this rho is, we call it as resistivity. So resistivity is something that explain about that material. Example, if I use platinum for my resistor, or if I use copper for the resistor, that's the value changing according to the material, right? So then these two materials has two different resistivity. So now you see that R is manufacturing constant that you can change by changing these three variables. Those are the parts that we're going to work on the worksheet. And in addition to that, we discuss about the power a little bit in this chapter, in this lecture, right? So power, we use uppercase P for that. And power is basically work done per unit time, as we discussed in your physics 116, right? So when it come to here, work done, you can write by using voltage and the charge. You remember that the voltage is work done per unit charge. And by putting everything into here, you will be able to write this as I times V, right? In addition to that, since V, by using Ohm's law, since V equal R and I, we will be able to write this as I squared and R, and also I will be able to write this as, by plugging I into there, I can write V squared over R. Any of this formula according to given information will be useful to calculate the power, right? So measuring by units of watts. Power is measured by unit of watts. So now, in addition to that, I discussed a very important thing in here about the RMS value. RMS values, we call it as root mean squared value. Because the reason is, if you are using DC means direct current, direct voltage. That means you basically have a graph, something like if I plot the current as a function of time or voltage as a function of time, this is just staying as direct. In that case, whatever you are measuring by using multimeter at your laboratory, that will be directly the voltage and the current of the circuit. But the problem is, if I do it AC, current or voltage, AC, this is DC one, this is for the AC, then you know that it is a sinusoidal wave that you're going to get a wave like this, right? So now the problem is when you use multimeter to measure the voltage of AC circuit or AC current or AC voltage, then your multimeter will not give you the correct answer. What your multimeter give you is the root mean squared value, right? So now how do you connect these two? That's the important thing. So now if I have, we'll say this is voltage, this will be my maximum voltage or peak voltage, we call it as, right? So now VRMS value is something sitting in here that's kind of RMS, root mean squared value. That is kind of like average, but it is not exactly average. VRMS is call it as the root mean square value. That will be your peak voltage divided by root 2, right? So this VRMS value you measure by using multimeter, but real value of the circuit is, you see that it's keep changing, that will be your peak voltage that will be able to measured by using the whole signal. You will be able to measure it by using oscilloscope in the laboratory. So we don't usually use in your laboratory oscilloscope, but we will be able to see that whole wave voltage is keep changing with the time on the oscilloscope. Okay, only thing you need to know how these two going to connect each other, and what you are measuring in AC signal is VRMS value, not a peak value. Okay, so that's mainly what we discuss in this chapter. And in addition to that, we discuss about junction rule little bit. And I will come back to the question with that, and this will be basic summary we discussed. Okay, so now let's move into, don't know what happening here. Okay, let's move into the question number 1. Let's move into the question number 1. So now question number 1 is actually talking about the light bulb, how resistance changing with the temperature, right? The variation in electrical resistance with the temperature can be used to make a precise temperature measurements. Platinum is commonly used since it is a relatively free from corrosive effect and has a high melting point. I think I copied this question probably from your textbook. And suppose at 20 degrees, the resistance of platinum resistance per meter is this much. So now let's think about how resistance change. So as we discussed, resistance is R value, right? So this is equal to rho L and A. I don't want any of this information for the question, but R is proportional to the resistivity, because in my lecture slides that I am talking about how resistivity going to change with the temperature, that will be exactly same for the resist. Okay, so the formula that we have, resistivity at any temperature, that you're going to find it out, is equal to resistivity initially that you're going to use, and then we have 1 plus alpha. Alpha we call it as the you see that it's given in platinum here, coefficient of the temperature coefficient of resistivity, that is the alpha is here, temperature coefficient of the resistivity, and then we have temperature change, right? So this is for the resistivity. Since they are proportional, as soon as I write this formula, I can write it for the resistance, 1 plus alpha and delta, it's delta the temperature change, right? So now let's see what is given in the question. So definitely you see that here, suppose at 20 centigrade resistivity of the platinum, the resistance that you are using is 164.2. That means you know that your temperature, T initial temperature is 20 degrees and R naught is 164.2 ohms. And then when place the particular solution, the resistance is increased into that. So now R will be 187.4 ohms. And what's the temperature of the solution? Coefficient of resistivity is 3.93 times 10 to the negative 3, negative 3.1 over centigrade. Okay, so now we have those numbers. We just need to plug it and find what is my final temperature is. Okay. So now let's everybody know what is the delta T is, right? Delta T is the change of the temperature, right? So my final temperature, you see that resistance is increasing. I'm going to write final temperature minus initial temperature, T naught, as I write it in there, KOTI. Okay, so now we can plug the values. Okay, so R is what I need to find T final. So let's put this one into, before plugging in, let's see that if I can simplify this to find the T final. Okay, so R equal, it's totally up to you how you're going to do it. I'm going to multiply R naught times this and multiply this time this, right? Plus R naught alpha and change of temperature, T final minus T naught. But I need to find T final. I'm going to subtract R naught from both sides and divide by R naught alpha. And then I will be able to write this like this. R minus R naught and going to divide by R naught alpha. And then you will left T final minus T initial side. What I need to find is T final. Right, T final, solve for the T final, I need to add T naught into the both side. So then I have T naught plus R minus R naught divided by R naught and alpha. This is where that I'm going to plug the values, right? Because then I can see what if I do any mistakes before plugging the values. So now T naught is 20 degrees plus R minus R naught 187.4 minus 164.2 and going to divide by R naught 164.2 times alpha 3.93 times 10 to the 3. So since everything is in SI unit, the final you're going to get from centigrade. Okay. So let's see what the values I have. I have around 56. I would say this is also 56. I add 1.664 to make it correct for everything. Okay, so 56 centigrade. That will be my question number 1. Okay, so now let's move into the question number 2. Question number 2, I want you to experience by changing your cross-sectional area of the cylinder and also by making hollow shaped cylinder, by making solid cylinder, how you're going to change the resistivity. Okay, so now let's go and check this. The figure below shows the cross-sectional that your length of the cylinder is long one. It is pointing into the board that we basically have same for everything. So it says 3 long, same length, right? We're going to use it as L for all of them. And also it says same material. When you say same material, you need to read very carefully in physics problem. There are many problems you can make by using same question, right? Because of that, my understanding, my view of watching you is by changing the things. Can you actually do new things? That's the idea. Okay, with circular cross-sectional of edge as shown. This is a cross-section. And conductor B, outer radius 2R. So you have outer radius 2R in conductor B. So let's label those. Conductor B, here I have 2R. And will fit snugly within the conductor A, outer radius 3R. So conductor A has outer radius 3R. As soon as I say snugly within the A, right, that means you can put the B inside this white area. So what that means is this will be 2R. Okay, and now I have conductor C, radius R, and it also say it will fit snugly within the conductor B. As soon as you understand that, then this will be R, right? That's the information you need. Now rank the 3 conductors according to their end-to-end resistance. Whenever I say the ranking, it's very important. You need to use this notation for ranking. by using A, B, C given. Otherwise, I don't know what your answer is. Write everything that you understanding very clearly to someone who don't know what you are doing, right? So that will explain a lot about your learning process. Okay, so now we have everything labeled in here. So now what we know is we can write resistance is equal resistivity times L over cross-sectional area. So now we're going to write this for A, B, and C separately, right? So now rho and L are the same. Cross-sectional area, we know that cross-sectional area of a circle or your font view of that, or the cross-section area, if it is a circle, then we know it is pi r square if circle has radius r. According to that, we're going to use it for the A, B, and C. Okay. So now let's do it for the A first. Okay. So now this R is for the resistance. The R, I have it in here. This R, this is radius. Okay. Probably I can change it to lowercase r if I need, but I'm going to use as it is. Okay. So R for the A case, I'm going to write that's resistance of the A cylinder, right? So that will be equal to rho L is the same for all of them. And then I need the phi r squared. That means this black area I need to find. How do you find that black area? So you have 3r radius circle and you have 2r radius circle inside. In between area of these two will be 5, 3r squared, right? Let's write it here. 3r squared minus, that's the area of whole A, but you need to subtract the inner cylinder from that. Then I have 5, 2r squared. All are in the denominator, right? So now, after you do that, you can do the, you can simplify it here, RA, right, rho L is there. But on the denominator, I have, you know that this is, will be, let's write in here, 5. I have 9r squared minus 5, 4r squared. So that will give you for the A. The first time do it like that, then you understand it. Don't like jump and say this is greater than the other one. It's not definitely correct when you do that. 9 minus 4 is 5. 5r squared. So I found it for the A, right? So now you can do the same for the B and the C. So B, RB equal rho and L. Now your value will be cross-sectional area will be larger cylinder, that is 2r power 2, and then inner one 5r squared. So now solve this, do the same procedure, and then you're going to get rho L over 3 5r squared. Then you do the other one is the easiest one. So third one, RC equal rho L over 5 only r squared. So now I have these 3 formulas, right? So now by watching these 3 formulas, you will be able to rank it. So now which one is greater? Whichever one I have larger denominator, that will be the smallest one, right? Because of that, your ranking will be RC, RB, and RA. Okay, so now that's it for that. And also you can think if you have a rectangular shape wires, if you have square shape wires, you need to think this area is not this one when you have different shape. This is only for the cylindrical, cross section is circular, right? If it is the square, then you know that how to find the square shape area. That will be side length double, right? And O squared, I mean not double, squared. So if you have side length A, your area will be A to the power 2. If you have rectangular shape, your area will be A and B, right? According to that, you should be able to modify this question into different form of the questions. Okay. Okay, now let's move into the number 3. The figure shows the portion of the circuit. What are the magnitude and direction of the current I in the middle right wire? See that I here? This is what I need to find it out. So this is actually, we will come back to this another part of the your semester. This is, we call it as junction rule. Junction rule basically saying your current is a constant, that saying charge are conserved. Another way that we discussed earlier, this is another way to say is your energy, the charge conserved, right? So now to do that, you know that junction rule is saying if I have current, you can have junction, many junction in your home circuit, right? They are connecting to different wires. If you see the connection, it's very complex that we even cannot identify those wires. But we're going to like get in some understanding. If you have a junction, this is called it as the junction, right? So now junction rule saying any current coming to the junction, we'll say it is current in, should be equal to the current going out. So we'll say this is also current going out. Let's say I1, and this is also current going out. So junction rules say in this I, let's use I instead I in. So current in equal current out. According to my diagram, it will say I equal I1 plus I2. If they are, you see that they are representing outward direction from the junction. This is into the junction, in equal out, right? So that's the rule that we're going to do, use for to solve this problem. So this is a kind of puzzles that you're going to select, or maybe kind of game that you are thinking, right? So now when I use junction rule, I need to identify where to start. Starting point, you need to decide, right? How you decide? So usually if you have 3 wires in the junction, you should know at least 2. Then the other one you will be able to find it. If you have 3 wires, if you have 2 unknowns, that is not good place to start, right? So now if I directly jump into this junction, you know that I have many wires that I do not know the current. Because of that junction is not my first junction that I should try, right? According to that, you need to think very carefully which junction you're going to start. So now best way to start with the ending of your beginning of your circuit or ending of your circuit. If you see 2 unknowns, one unknown, 2 knowns, then you can start, right? Here you can definitely start somewhere here if you would like to go first junction, or else you can start in here because you see that 3 known, 1 unknown, right? You should have only 1 unknown in the junction to start, right? I'm going to start with the junction that I label as here. Okay, so let's start from there. Here is this one. Okay, in this junction, you need to understand junction is here. 3A coming to the junction, 2A arrow direction, come to the junction. So the junction, the wire that I have it in here, no current, no show in the current. That means I need to draw the direction of the current and then decide how much is, right? So 3 plus 2 is 5. 5 is coming in. That means from this junction, I have 5 going out. I'm just write the 5 because if I write the A, it may be not visible. Okay, so that 5. So now Now you understand that 5 is going out. That wire has the 5 current to the right direction. After you complete that one, you can move into this junction here, right? Then you can find the value of the bottom wire if you want, right? So let's do that. So I'm going to move into this junction now. This is the junction I am working. So now you see that this 2A going out from the junction, this 5 is incoming current to the junction. That means this small piece I have it in here should have outgoing current. 5 is in, 2 is out. Because of that, this should be also going out 3. Okay. So now, after you understand that, you can move into the top junction or the bottom junction. I'm going to move into this junction. So now when I watch this junction, I have 3 incoming, 4 also incoming to junction. Now I know that there should be something out. Out will be 4 plus 3, right? So that means this junction I have 7, right? So still I am not ready to go to this junction on the right because I have 2 unknowns. Now I need to move to the top and complete that puzzle and then come back to the junction that we need the current. So now we're going to move into this junction now. So now when I move to that junction, I have 4 wires. 3 wires has the current, 1 is unknown, right? So now you see that this all 1 amps, 2 amps, and 2 amps all are incoming current to the junction. That means my other wire should have the outgoing current. 2, 2, 4, and 5. So that means this wire should have current this direction. That will be 5 amps, right? So now I am done. Now I can find the current on the I mentioned on the diagram by taking last junction. So now this is the last junction. So in that junction, you have 4 wire pieces. You know the 3 of them. You need to find the unknown I, right? So now you need to identify 7 and 5 coming towards the junction and 8 is going outward. They are not equal. 7 and 5 is 12. 8 is the only out one. Then that means I should have another outgoing current that should be 4, right? Because 7 plus 5 is 12 and 12 minus 8 is 4. Okay, so your answer is I equal 4 amps to the right. Okay, let's move into the question number 4. In question number 4, it basically working with the length and the radius of the cylindrical resistor, how you're going to calculate the resistance or how you're going to compare these resistance. Let's read it. A conductor of radius R, length L, and the resistivity rho has the resistance R. So what that means is the formula that we know, R equal rho L, and radius R means cross-sectional area is pi R squared, right? Now it is melted down. So you have, let's draw it. You have a resistor like this, which has radius R and length L and resistivity rho. And then you melt it down. You melted it down and form a new conductor, also cylindrical, with 1/4 of the length. Okay, so it seems that the length going to be decrease into 1/4, right? So when length decrease, there is some important information happening in here. So now let's say this is length over 4. And now you have new radius. I'm going to say R1, right? So because the reason is you melt or maybe you freeze. So melting is basically expanding anyway. So now when you do change the, basically you change the shape, but you do not change the volume. You keep the volume constant. melt or freeze. According to that, it's going to change the shape, right? So in this case, it is still a cylindrical shape, but because since the L change into L over 4, then radius should be get larger, but we need how much it is. But now I need to find the resistance of the new one in terms of R given, right? So now new one I'm going to write, let's write R in for new. R new, or you can say R1, it's totally up to you. And you're going to change the length into length over 4. So then 4 go to the denominator, and then I have 5 and R new squared, right? So I know how to connect R and Rn if I know what is R new is. So now to find R new, this is you need to process very carefully. So this volume and this volume should be equal to each other, right? So volume of this one, we know that we can write the volume for the cylinder, that will be cross-sectional area times the length of the cylinder. And here also same formula, but since I have new radius and new length we know L over 4, you have this formula. But these two should be the same, right? Then you can find the connection between your old R and the new R. So let's write down them, making equal and find the connection. Equal pi R new squared L over 4. As soon as you write this, L cancel out, pi cancel out, right? So if I cross multiply, I know I can write 4R squared equal R new squared. Is that I need? Yes, because I need R new squared in there. R new squared equal 4 times R squared. So after you find this, you go back to this formula and rewrite this formula. Let's rewrite rho L and 4 and 5. R new squared is now 4R squared. 4R squared, right? This you can simplify. Rho L over 5R squared, but you have 16 on denominator. So now as soon as you see this part, you will be able to understand R, right? So that means R new should be 1 over 16 coefficient is there, but then the rest will be your old R. So that means by changing this melting or freezing, you create a new resistor that has the 1 over 60th of the original resistor. Your length you decrease, and also you increase the radius. Decrease in length will be decrease the resistance, and increase in radius also decrease the resistance. So because of that, your new resistor have 1 over 60th R. Okay, so now let's move into the number 5. So number 5 is very simple, that we need to work with the power. So calculate the resistance of 40 watts automobile headlight designed for 12 volts. So resistance is the one that we need to calculate. This is the power is given. This is the voltage is given. So now you need to decide which formula you can use. So power will be, remember that power is one way, you can write I and V and use the Ohms law, replace the V with the R, or you can replace the I with the V, right? I'm going to replace the I with the V because voltage and the resistance is the relation I need. Okay. So now I need to find the R. According to the question, I do the cross multiplication, power, no, I will do the cross multiplication, and I'm going to find the R from the formula. Write the R from the formula first, and then you can plug the values. So R equal, you see that cross multiplication and P goes down, that means V squared over P, right? So everything is given in SI units. This is 12 volt power 2, and power is 40 watts. So then you're going to get the resistance in ohms unit. I have around 3.6 ohms. So there is no correct sig fix. If I need to do it correct sig fix, I should give you actually this is 12 volt, this is 40 watts. Then I have division. Each of them are 3 sig fix. Maybe you can keep the 3 sig fix in here. Okay, try to use the sig fix on your homeworks, because all the homeworks you have correct number of sig fix. As much as possible, you should use it to practice your significant figures for this semester too. Okay, let's move into the number 6. Two light bulbs operate at 120, but one has the power rating 25 watts, while the other one has 100 watts. Which one has the greater resistance? So now to identify this one, you definitely need to know the power formula and how resistance connecting to the power, right? So because of that, we can use exactly so same formula that we have it on the top. So that will be V square over R. And then how the resistance change, R is equal, you can write it as the voltage power 2 divided by the voltage power 2 divided by the power, right? And then you know that you can do it for the two of them. Let's do it for the first one. I'm going to write R1. So you use exactly same voltage, 120 power 2, and then power is 25. And you do the same thing for the second one, 120 power 2, and now you have 100 watts, right? So now, which one has greater resistance? It did not ask you to calculate ratio or anything. You know that whichever one has the lower denominator has the greater resistance. Because of that, R1 is greater than R. Okay, that's it for that. If I did not ask about the ratio, you don't want to find the ratio. But if I ask you the ratio, make sure that you find it. Or if I ask you to compare it, find it. But here I am asking which one has greater resistance. Because of that, you just need to say which one is greater. Okay, so now what SI unit for electric bill you are paying for? I think I discussed this in your lecture also. Do you pay for the power or energy? So we are paying for energy. So we are paying for the energy, not for the power, because the reason is the units that we are paying is SI units. So that basically kilowatts hour. This is the units that we are paying for the electric bill. How many kilowatts hours we use it. So now you know that this part is power, right? And this part is time, right? You remember that the power is defined as work done or energy divided by the time. So if I multiply this 2, that means I am paying for the work done. So that is the energy. So we are paying for the energy, not for the power. Okay? That's the units that we are paying. That's right. Okay. And let's move into question number 8. So now in question number 8, when a potential difference is applied to a certain copper wire, current is 1.5 passes through the wire. If the wire was removed from the circuit and replaced with, again about the resistance, replaced with the copper wire with the twice diameter, what current would flow through the new wire? Assume wires are identical in all the other aspects. Okay, so now we know that we can write, we need to find what current, right? We know that the R equal rho L over A does not have the current, where the current coming is Ohm's law. So Ohm's law is saying that V equal I and R, right? So now if I use the R into here, you know that I can write this as current times rho L over A. R I'm going to replace with the resistance information, right? So now if I use it for the first one, I know current is given, but I'm going to write it as I1, that is for the first one, and rho and L is there, and then I have phi and radius squared. Right? That is for the case number 1. So now I know that the same formula, but when I come to the second one, let's label it as V1 and label it as the second one. Second one, I have the current. Now I have the new current, I2. Rho is still the same. You say that identical in all other aspects, right? So then your L also same. Only thing is you change the diameter of the wire. That means half. So you have 5. And now you're going to, you see that copper wires twice the diameter. If you make a diameter twice, this is twice, right? This is the diameter. That is 2r basically. If you make it twice, that means you make it 4r. That means you make the radius 2r. If you do not understand, please ask during my office hours. So your radius will be now 2r and power 2, right? So let's simplify this. I2, rho, and L. We're going to do 2 times 2 is 4, 5, and r squared, right? So now, since we are connecting this into the same potential difference we're going to apply by using the power source. That means these two going to be same power source, same, right? So now I can make them equal. I'm going to write I1 equal rho L over 5 r square should be equal to I2 rho L over 4 5 r square. So now you see that these parameters cancel out, this will cancel out, this also will cancel out, right? So only what is left is I1 equal I2 over 4. What that means is I2 is now changed into 4 times of I1, 4 times of I1, right? So now the answer will be 4 times of the I1. Since I1 is given, we can calculate the I2. So I2 will be 4 times 1.5. Okay, because of that, I'm going this way. I2 will be equal to 6 amps. That's my final answer according to the section. Okay, my last question about the RMS and peak values information, right? So now what is the value of the peak voltage and VRMS value, right? See that what is the value of the peak voltage for AC power supply? So that value I have it in here. Oops, no, this value I have it in here is VRMS value. VRMS equal 120 volt. Okay. So now I need to, what is the peak power consumption rate of a 60 watt AC light bulb? So I need to find the peak power consumption value. That means I need to find the P naught value, right? I need to find here V naught value, and I need to find P naught value, and this is given as your P R M S. Okay, let's do the first part first. First one. Okay, I have the VRMS value. I need to find the V naught. So you remember that VRMS equal V naught over root 2, right? Then you can calculate the V naught. V naught will be root 2 times VRMS. Peak value is not able to observe in your multimeter. That will be observed by using your oscilloscope in AC signal. Okay, so this value is equal to 169.7 watt. PRMS given and we need to find the P naught. But be careful, PRMS is not equal to P naught over root. So this is wrong. Okay, there is no that relation. PRMS equal P naught over root 2. This is not correct. Okay, so check how we going to connect these two first. So you know that you can write PRMS by using VRMS and IRMS, right? So this formula I write in here will work for the current and the voltage. That means if I want to write for the current, RMS of the current will be able to write I naught over root 2. So now these two formulas valid, but this is not. Okay. So now we're going to combine this. VRMS will be V naught divided by root 2. IRMS will be I naught divided by root 2. So now you see why that formula is incorrect. This will be V naught I naught divided by 2. So that is the PRMS. Now V naught and I naught, we know it is power 0 divided by 2. Right? That means you see that PRMS new formula is P naught over 2, not the root 2. Okay, so now P naught will be twice times PRMS. That will be 2 times 60 watts given. Because of that, P naught will be 120 watts. Okay, so that's it for this worksheet.